Today I'll be talking about trigonometric integrals, and my intention is that you have gone to my website and printed out these notes so that you can follow along and write on them with me. So if you need to do that, pause the video, go print them out from my website, and then unpause it. So these are about techniques to do integrals involving trigonometric functions like sine and cosine. So like anything else with trig, you need to have a lot memorized in order to do these. Here's the minimum you need to remember from trigonometry to do these integrals, and I've printed it all here. First, you need to remember how to express tangent, secant, cosecant, and cotangent in terms of sines and cosines. So for example, tangent x equals sine x over cosine x. You also need to remember this Pythagorean trig identity, sine squared x plus cosine squared x equals 1. And there are two others that you can derive, for example, by dividing each of these terms by cosine squared x. You get another one involving tangent squared and secant squared. But this one you have to know. You probably do know that actually already, but something you probably don't have memorized are these two so-called half-angle formulas expressing sine squared and cosine squared in terms of cosine of 2x. But those are super useful for integrals involving powers of sines and cosines. You also need to know all 6 derivatives, the derivative of sine, cosine, tangent, secant, cosecant, and cotangent, which I've printed here, like the derivative of sine x is cosine x, for example, and also all 6 antiderivatives. I'm saying really 4 because pretty much everybody knows that if the derivative of sine is cosine, then the antiderivative of cosine is sine, for example. So the 4 that people don't remember are tangent, cotangent, secant, and cosecant, which I've printed here. And you could derive these when you need them, but it's much more handy to just sit down for 2 minutes and memorize these so you can use them in the course of these longer problems. Now we're actually ready to learn some techniques for doing trig integrals. So the next page of notes has them printed all there for you. My advice is that to do trig integrals, first try simplifying them or using a u substitution. But there are some special cases where you need special techniques. Here's the first one. To evaluate integrals of powers of sine and cosine. It depends if the powers are odd or even. So first let's say that n, the power of cosine x, is odd. You want to separate one of the cosine x's from the rest. You're going to use this Pythagorean identity, cosine squared equals 1 minus sine squared, to write all other cosine in terms of sine. And then you're going to make this clever u substitution, u equals sine x. And I'll do an example of this in a minute. Similarly, if instead of cosine x being odd, if the power of sine x is odd, you follow the same procedure, but switching the role of sine and cosine. Now what if neither power is odd? Then you have to use these funny half-angle identities, which I printed on the previous page. Similarly, if it's powers of tangent and secant, there's a similar procedure to powers of sines and cosines. See any textbook, or you can look up some examples online to see how that's done. But it's a very similar procedure. And then there's another special case that is a totally different thing. What if instead of powers of sines and cosines, it's sine of multiples of x, like sine of m times x, cosine of n times x, or things of that nature. In those cases, you have to use these very unusual identities that pretty much no one has memorized. But follow this chart for which ones to use in which case. So we'll do an example of this too. So let's go to the next page and do an example. Here's the first example. Sine to the 4th x cosine cubed x dx. And this example will follow the instructions from this box. In this case, indeed, n, the power of cosine x, is odd. So we're going to separate one cosine x from the rest and use this thing, cosine squared equals 1 minus sine squared, to write all other cosines in terms of sines. Let's do it. Here's what I mean by separate one of the cosines out of these three from the other two. I mean like this. Now we're going to make the Pythagorean trig identity, cosine squared equals 1 minus sine squared. We're going to substitute that for cosine squared x to change all other cosines other than this one that we pulled out. Change them all to sines. So now we have only sines. Now we make this u substitution on the side, u equals sine x. So again, I'm just following the steps here. Here we're on step 3. U equals sine x. And watch what happens. If u is sine x, du must be cosine x dx. And lo and behold, cosine x dx appears. So we can now change everything to u's. Sine to the fourth x is u to the fourth. 1 minus sine squared x is 1 minus u squared. And cosine x dx, the whole thing just becomes du. And now, this integral is easy. We can now do u to the fourth times 1 and u to the fourth minus u squared. We've distributed the u. And now do the antiderivative. Antiderivative of u to the fourth is u to the fifth over 5. And similarly, antiderivative of u to the sixth is u to the seventh over 7. Plus c. Now we're almost done. We just have to change back from u's to x's because the original problem was about x. So we use this, u equals sine x, and we say that's sine x to the fifth, which we write as sine to the fifth x, to avoid confusion. And we are done. Let's do another example of a trig integral. Let's do this one. Sine of 8x times cosine of 5x dx. Notice these are multiples of sine and cosine, not or multiples of the x, not powers of sine and cosine. So we're following this box on the previous page of notes, and we're in this case, sine mx cosine nx. Here the m is 8 and the n is 5. So we're going to use this. Sine a cosine b equals this whole mess. So in this case our a is 8x and our b is 5x. And we're going to follow, it's going to be half sine a minus b plus sine a plus b. So let's do this. That's a half sine of a minus b, 8x minus 5x, plus sine of a plus b, 8x plus 5x. And let's see what happens here. If we pull out the half, we get a half integral sine 3x plus sine 13x dx. Now this is much easier to do. Now you could do a u substitution here, but it might be valuable to just pause and think about in your head what would happen if you did that. What would happen if you did antiderivative of sine 3x? You might be tempted to say the antiderivative of sine 3x is negative cosine 3x. But you have to remember, because of the chain rule, if you did the derivative of negative cosine 3x, it would not be just sine 3x. It would be sine 3x times 3, the derivative of 3x. So to compensate for the fact that there's no 3 here, you need to stick a 1/3 in front as a coefficient. And you can convince yourself that the derivative of negative 1/3 cosine 3x is in fact just sine 3x. Now, if you're uncomfortable with that kind of reasoning, then go ahead and make the u substitution on paper instead of in your head, and you'll get the same answer. But if you do the same reasoning for sine 13x, you'll get negative 1/13 cosine 13x. And then we just need to clean this up. We get negative, distributing the half, we get negative 1/6 cosine 3x minus 1/26 cosine 13x plus c, and we are done. Now, at this point, you should do these on your own and make sure you can do this type of problem and then do whatever homework has been assigned to you.